This evening I published this circuit. So let's take it apart. And I thought that this schematic was derived from a circuit of the 1970s, etc., etc. And I made it suitable to work with, say, a ground connection or a grounded earth. So that's the reason why I mounted here this 1 microfarad cap and a 1 kilo ohm resistor. But much more interesting is, in my idea, the original schematic of the 1970s, like it was published in that old ETI Magazine, and that's here. This is, say, a real circuit for experiments. When you are a little bit acquainted with electronics, you will see that this is a constant current source. At least that's what they tell in the magazine. And here we have that multi-vibrator. In fact, it's the same circuit. You can compare it. But I found, to my surprise, extremely good properties of this 1970s circuit, and then especially regarding the waveforms. They were very pure, but of course when you look closely to this schematic you see that the waves are generated opposite to a resistor here. So we have a DC out here. That's something to take in account. No coupling capacitor or so. And here we have also a DC out. And there is no ground in this circuit. So you cannot take directly this this waveform opposite to ground. Only between, say, the pins of the capacitor here. That's where we take the signal out. Perhaps there are possibilities to use a field effect transistor because it's high impedance on its grid. Anyway, or here also, I say grid, but I mean gate, of course. Perhaps it's possible to take this signal out opposite to ground via a field effect transistor, and also here. I didn't do that, that will take a lot of time, but I was more or less very, very surprised by the good properties of this original 1970s generator, generating square waves and triangle waves. And of course we know that we can in a certain way easily change a triangle wave into a more or less sine wave. There's information about that on the World Wide Web, perhaps also on YouTube, I don't know that. We need in that case a certain capacitor with a certain value, so that these sharp triangle waves get more or less rounded and mimic a sine wave. Anyway, I will again now show the properties of this 1970s circuit. Of course I have to put on the scope. And let's see what are the possibilities. And I do it again with only 2 capacitors, say, to give the maximum and the minimum frequency. So I was very, very surprised to find this perfect here triangle wave, all 671 kilohertz in this circuit. And of course when you test that with the scope, make the connection in the proper way, minus or positive of the scope, say the input and the output. Perhaps you don't see the waveforms when you reverse the probes of the scope, but anyway, that's not very important. So now we are on the, say, 698 kilohertz. I think it's a very good waveform. So let's look again. There are here a lot of bibbers. We have to take them in account in that way. It is not ideal, the bibbers. I don't know where these bibbers come from. Could have to do with the power supply, with the transistor types, etc. So now I go to the lowest frequency by pushing the switch. Let's see what happens. Is there still a wave? Well, yes, there is still a wave. And we are now on 26 Hertz. By the way, the bibbers that you see here are in a certain way always on my scope. Not always, but sometimes, and perhaps they are caused by stray fields that enter my circuit, etc. So 26 Hertz, very proper triangle wave. So it's absolutely worth to try this 1970s circuit. Now I'm going to show the square waves, and the square waves are taken out here on the positive lead, and the I say parallel to that 300 ohm resistor. And I was again more or less flabbergasted by the pureness of these waveforms. Here they are. The only idea, and in my opinion a problem, but when you are better acquainted with electronics compared to me, there must be a way of taking this very pure square wave out. It's more or less flawless. And let's switch now to the highest capacitor value. So now we are here. Let's look what the waveform now looks like. So you can surely see that on this high frequency, much higher compared to the 555 chip, it's 836 kilohertz, and the waveform is still a square wave. It means that you must nothing, but anyway, you can make a kind of buffer stage connected here and connected here. Here is the square wave output, here is the triangle wave output. So let's go to the schematic. Say for both situations here, here and here, we need a buffer stage with an extremely high impedance. So that's the reason why I think and tell in the description that perhaps a field effect resistor can do that job. So here and here, an output buffer made with a very high impedance input to take all these beautiful waveforms related to only one capacitor here out. That was more or less all to tell. Thanks for watching. And let's again look to the beautiful waveforms. Say where a multivibrator with a constant current source can produce such a good waveform on 837 kilohertz. I'm more or less sure that the 555 chip cannot compete. Thanks for watching.